Sorry for the late start. Apparently we got our signals mixed about who was going to be introducing Chris, but I will give you a quick introduction because that's about all I have. Chris Cappa graduated with his undergrad from Hope College. I'm going to check with him. He got his PhD at Berkeley. He then did a postdoc at NOAA, and now he is at UC Davis. And I've known Chris for how long now? Probably about 8 years. And he's a fantastic scientist who's now going to talk about simulating secondary organic aerosol at varying levels of complexity. Okay, and you've got your own mic.
I do. Well, first of all, thank you to Alma for inviting me out here this summer. It's been a really great visit. Get a chance to hang out at NCAR for a month. And so what we've been working on since I've been here is kind of further development and refinement of a newish model of secondary organic aerosol formation. And I'm going to try to put this in the context of kind of what it currently exists with respect to simulation of secondary organic aerosol and where I think it can be useful. But I always like to start with acknowledgments because I always forget to at the end. Number of people. So Kevin Wilson and I, the model I'm going to talk about today, we co-developed this. We've been working together for many, many years. And so he's definitely a key contributor to this project from the inception. John Seinfeld and the Seinfeld group have provided a lot of the chamber data that I'm going to talk about today. And then my colleagues here at NCAR who've been just really fantastic to work with in providing a lot of information from the Gecko model that I'll talk about. Paul Zeman, who's helped me think through some questions related to wall losses in chambers that we'll talk about. Shantanu Jathar, who's a postdoc at UC Davis, who helped me find a bug in my code. That was very important as we've been moving things forward to 3D modeling. And Mike Kleeman, who's also been helping in our moving forward towards 3D modeling using the model that I'm going to talk about today. So just a quick outline of what I will talk about. So first, again, the talk is focused on secondary organic aerosol. Talk a little bit about the various models that exist and the levels of complexity that they comprise. And then I'll talk about the model that we've developed, which we call the Statistical Oxidation Model, or SOM. I'll give a model description, do some comparison with and fitting to experiments to show how this can be used, and then talk a bit about what I've been doing here in terms of developing our intermediate complexity model in the context of a more complex model in order to try to make it more robust and capture a bit more realism, which you always are going to lose as you start to reduce complexity. And then I'm going to ask a question about just related to experiments in general of SOA formation in chambers, and ask the question, how complete are these experiments, and can we assess this through model considerations? So I'm sure most of you know, in case people didn't, I wanted to give a very quick background. What is SOA? It's particulate matter formed from condensation of oxidation products of volatile organic compounds, or you could have condensed phase chemistry as well, leading to the formation of SOA. But the general picture is we have a VOC plus an oxidant, some stuff happens, and you get SOA. SOA, one reason that we care is it is a major fraction of global sub-micron particulate matter. So we want to be able to represent its concentration and global distribution appropriately. Reasons for this, at least from climate perspectives, it's important for particle growth in part. As you have condensation of SOA, your particles are growing. This can affect the concentrations of cloud condensation nuclei. It can affect the hygroscopicity of particles because it's typically lower, doesn't like water as much as inorganic compounds. And one of the reasons that we're particularly interested in SOA today and focused on understanding it further is that the existing models that we have they tend to underestimate the concentrations of SOA in many regions, but do overestimate it in others, such as the very far upper remote troposphere. And so some questions that I have is this a limitation of model formulations? Could this be missing SOA precursors? Is it something else? And so we're going to take a little look at SOA models to try to understand some of these issues. So when we deal with SOA, what are we dealing with? Let's take a look at this process in a little bit more detail. So if we're thinking about, in this case, predominantly gas phase formation of SOA, we start with some compound here, N, and I've just taken this figure from a paper by Jose Jimenez. We start with some compound here, and it's going to react with some oxidant. What's going to happen along that way? Well, maybe you'll add functional groups. That'll tend to, in this case, lower the volatility. So this axis here is volatility. And so you might add functional groups, usually adding oxygen. So your oxygen to carbon ratio is going to go up, and your volatility goes down. That's going to make a compound more likely to condense, right? You can also, then some reactions are going to cause molecules to fall apart. We might call that fragmentation. That's going to typically lead to increases in vapor pressure as things fall apart. May also increase your O to C as well, because you might still get oxygen addition during that process. You can also have condensed phase processes occurring in which you have accretion reactions going on, so molecules within the condensed phase getting together, forming a bigger molecule. That's going to tend to decrease the volatility. It might increase or decrease the oxygen to carbon a little bit, but the key aspect is that it decreases the volatility. And just because Sasha's here and I've been talking with him a lot, we can't forget about photolysis. Photolysis is going to cause things to generally fall apart and increase the vapor pressure potentially quite a bit. Possibly add oxygen, possibly lose oxygen on some of those molecules. But this is the basic chemistry that we need to represent when we're trying to deal with SOA formation. And so one way to look at it, this is how I like to think about it. We have a VOC, we might react it with OH, we make some things. We have two things, those things might react with each other, we'll make some more things, and then we'll make some even more things. Right? We're making things. And the question is, what are those things? What represents the transitions between these things? Right? And how do we predict the properties of those things as they relate to SOA formation? So how are we going to deal with this complexity? There's a couple different ways. One is what I'll say we could embrace this complexity. And this is going to be models like the GECKO-A model that I've been working with Alma and Julia on here. These are models that tend to try to represent the chemistry as explicitly as they can. The difference between these two, this one's very explicit, this one's kind of explicit, but you're trying to deal with some level of explicit chemistry along the way. So that's one approach. Another is to ignore as much of that complexity as possible. And that's the type of thing that the very successful, for many years, 1 and 2 product models would do. You have some compound, it reacts, it forms 1 or 2 things, and that's it. And that's things like what the volatility basis set also does if it doesn't have additional chemistry in it. And so these, I would say, tend to ignore a lot of the complexity that's going on and try to parameterize their way out of this complexity. Or some models try to fall somewhere in between, trying to capture some of this complexity, but not deal with it explicitly. And these are going to be things like if you add aging reactions to the volatility basis set, and we'll look at what that means in a minute, or other variations on the volatility basis set. Kelly Barsanti and Jim Pankow have introduced a method here that they call the carbon number polarity grid. That's another kind of intermediate complexity model. Or we have an approach that we're taking here that we call the Statistical Oxidation Model, and that's what I'm going to focus on today. But before getting to the Statistical Oxidation Model, I just want to give some additional background on kind of these more complex and less complex models so we can see where it fits. So if we have something like the GECKO-A model, and this is taken from a paper by Bernard Amont a few years ago, you start with some compound here, you have your parent species, and the way that it works is it generates, you react this parent species with OH, NO3, ozone, whatever your oxidant of choice is, make some peroxy radicals. These peroxy radicals can do some stuff. They might form some alkoxy radicals, and this goes on and on and on and on, and you basically try to generate or come up with all the possible reaction pathways that you can have, estimate the rate coefficients, estimate the branching ratios, and somehow basically represent all the possible chemistry that can happen within the gas phase. And then if you want to deal with SOA, what you do is you take these stable products and you allow them to partition into the particle phase based on some sort of absorptive partitioning theory. And so what you end up with, this is a really great picture that provides exquisite detail on all the species involved, things like functional groups that are very important to determining volatility of species. But it's too complex for things like 3D models because as you increase the number of carbons in your parent species, the number of species and the number of reactions that you need to represent goes up as a power law with about a factor, or I think the power ratio is something like 5.6 or something like that, if I'm remembering correctly. Basically, you have to represent millions of species if you really want to do this explicitly for large molecules. And there's ways to simplify this as well within the Gecko framework, but basically this is way too complex for 3D models. So what about simple models? Well, simple models, I mentioned this two-product model or a static volatility basis set model. Basically what they do is we have some VOC, we have some oxidant, they react, they give us one product, two products, maybe three, maybe four. We can choose our number there, and that's it. Those products are completely unreactive. They just stop. They may partition, though, into the particle phase with some partitioning coefficient here, K. And so what you tend to do with these types of models, right, they have no way of knowing what the chemistry is a priori, like Gecko. So you have to actually parameterize them by fitting them to chamber experiments. So you have experiments of SOA formation. You're going to fit the results of those of this model to those chamber observations, and you'll determine your branching ratios or your yields, sorry, and your partitioning coefficients. Now, these are very useful. They're very simple. They're very computationally efficient. They're currently the basis of most regional models. Global models are sometimes even simpler than this, but this is about as simple as you can get. But the key point is they don't represent any of this second generation chemistry. Chemistry happens once and then it stops. So it's not a very dynamic system, and that's really missing a lot of the details of what is actually going on. And it's going to lead to a not very robust solution necessarily if multi-generational chemistry is an important part of the SOA formation process, which I think things like Gecko have shown it is. So how can we start to add complexity? So just to give you some context for the way that our model works, here's kind of the currently most common, I would say, intermediate complexity model. And this is the volatility basis set that has added aging. And some of us were talking about this earlier today and try to give some context for this. So we have a VOC plus an oxidant again. It's going to give us maybe four products again. And simply, rather than these being static, we can have reactions. Here, say, OH, that's going to react with this product, and you can turn it from product 1 into product 2. Product 2 can go to product 3. We just kind of keep moving down this chain over time. Now, the problem with this model, as I see it, and people can argue with me about this if they want, is that the way that it's usually run is you have a VOC plus an oxidant, you get your four products here. Okay. Those products then, that is your parameterization. That is what people fit to chamber data. And they derive these four yields that inherently include the aerosol formation already. Then they go ahead and turn on aging, which is already part of these yields, right? It's part of the yield. And then you turn on aging and you make more aerosol. So not a surprise when you run this model, you make more aerosol compared to the static fit. But that shouldn't be surprising because you've basically turned on a mechanism to make more aerosol that is not consistent with the actual fitting mechanism that you've done. And so you find what I would call little discrepancies in the literature where people will, for example, for biogenic compounds, they say, well, we don't want to turn on aging because that tends to give large overpredictions in regional models. But then they say, well, for anthropogenic precursors, we're going to let those age, though. Right? You get these inconsistencies, and I think what we need to do is move away from that. And so what I would say is that there's a need for new physically and chemically based intermediate complexity models of SOA formation that at least inherently account for this aging as part of the model formulation. Okay. And so hopefully that's where my model comes in. So the statistical oxidation model, it's simple in concept, and we're trying to make it simple in application as well. Basically, we view chemistry as just a movement through a grid of species that are defined by the number of oxygen atoms comprising that species and the number of carbon atoms comprising that species. So we're going to ignore for the moment the fact that functional groups exist, and we're going to treat them in a very average sense. Okay, so we're going to say that each grid in this space is a species, and that it can be represented by some average properties of the species in that grid. Okay, so a species, as I refer to it here, is just CXOY, some combination of those. Then what we're going to do is we're going to allow for this species here, maybe this is our parent hydrocarbon, and we're going to allow for multi-generational reactivity through this grid. And we're going to allow both functionalization reactions and fragmentation reactions within this grid. And we're simply going to define properties of and rules for moving between all these species. And for now, at least, we're going to assume absorptive partitioning theory, which is kind of the standard of what everybody does. So just to try to show this graphically here, schematically, let's say we have this species here. Every species in this grid can potentially do something like this. It can, if this species reacts, say with an OH radical, it can add oxygen, it can add functional groups and increase its number of oxygens per species. But maybe some fraction of those reactions are going to cause the molecule to fall apart and fragment, which could add oxygen, could conserve oxygen, or could decrease the number of oxygens on one of those fragments. You're going to have 2 fragments from each one. And then other things that we are exploring is the possibility then that we actually also have oligomerization or accretion reactions causing these species to grow in size, which is going to tend to decrease their volatility. And so one species might start down here, some parent compound might start down here and react, and it's going to move and it's going to start to spread its way through this space as the rules that govern the chemistry of functionalization and fragmentation move it around. And the approach that we've taken is to take this model and explicitly fit it to observations in order to determine optimal parameters that describe this movement through the space for a given precursor compound. And we've come up with 6 parameters that we think can describe this movement reasonably well. These 6 parameters are, 1, the number of oxygen atoms that are added per reaction. Okay, so we can go from down here and we can add either 1, 2, 3, or 4, and that's some probability of addition. We have some probability of fragmentation, right? So when this species reacts, is it going to mostly go up this way or is it going to go that way? And we just describe that probabilistically. And then we also, because we're dealing with partitioning, we need to think about the volatility of the species involved. So we need to think about how basically the vapor pressure of all these, what is the vapor pressure of all these species. And so what we're going to define is the decrease in volatility that occurs per oxygen added. So you add 1 oxygen, what is the average decrease in volatility upon that addition of 1 oxygen? Okay. So our working paradigm here then in this model is that the properties of our species can be represented as a time invariant average of the various actual molecules that make up these species. Okay, this is an approximation. This is an assumption that's built in, and we're going to see how well it does. Okay, hopefully though for a given class of compounds, let's say alkanes, right, that the chemistry governing the oxidation is sufficiently general that we can simulate SOA formation across the entire class, basically across this entire grid, with really one set of parameters that will describe the oxidation of all those species in this grid. So for example, if we wanted to simulate anywhere between, say, octane and pentadecane, that we only need to determine one set of parameters, and we can figure out the evolution of the entire grid, and we can represent them all within that same one. And so that means that hopefully only one grid will be necessary per class, because we think that we'll need a different grid for kind of each class of molecules. And our hope is that although this is still complex, at least compared to two-product and the static VBS models, it may be tractable within a 3D modeling framework, at least for regional models. And we're working actually to put this into a regional model now. But of course, this does require careful attention to the formulation of our parameterizations that we have. And this is where the work that I've been doing here is very important, because by comparing with Gecko, we're able to get a better sense of how good these parameterizations are that we've been developing. Okay. So I'll start here then with an example. So this is some smog chamber results here in orange for alpha pinene plus OH under low NOx conditions. So these are from the Caltech chamber. So we just have the concentration as a function of reaction time. This is at about 2 × 10⁶ molecules per cc of OH. And the black line here is our best fit of the statistical oxidation model to the aerosol growth. And again, what we're adjusting is those 6 parameters, the 4 probabilities of adding 1, 2, 3, or 4 oxygens, the probability of fragmentation, and the decrease in volatility per oxygen added. Those are our 6 adjustable parameters in this model. And what I want you to take away is we can do a pretty good job of fitting the data, at least. However, maybe that shouldn't be too surprising, because there's a reason that the 1 and 2 product model has been used for so long, because it's actually pretty successful at fitting data. But my contention is that we're retaining more of the inherent chemistry in the system, and so that hopefully we're able to extrapolate outside of a chamber with greater accuracy or greater fidelity. But we can also get additional information. It's not just a fitting exercise. It's also trying to understand some of the chemistry and understand how well we're retaining some of that chemistry in our formulation. And so here's an example. This is just a bar chart of the probabilities. So these sum up to 1. So the probability of adding 1, 2, 3, or 4 oxygens per reaction with OH in this system on average. So this is averaged over the entire oxidation trajectory, and what best describes this behavior. And we see that for alpha pinene plus OH, we see that it's predominantly adding 2 oxygens per reaction. Okay? And in fact, that's not totally unreasonable in terms of the chemistry that is going on with alpha pinene plus OH. But we can do more than this now, because we have this time-dependent model. We can explore various things, such as I've emphasized that we're able to simulate the multi-generational chemistry. Right? It's not just first-generation chemistry anymore. All of our products, all of our species within our matrix are reactive. Okay, so we can look at then, for example, first we can look at the distribution of species mass within our space here, so number of oxygen atoms and number of carbon atoms. And so, for example, what we see here, so this is alpha pinene. It has 10 carbon atoms, and at the end of this simulation, what we see is that, so this is colored by amount of mass in a given bin. See that most of our mass is actually in these 2 bins, but we do have a spread of mass throughout all of these bins, and gray just means very, very low concentration. Okay, but here we see, for example, we have predominantly 4 oxygen atoms having been added net in terms of what dominates the SOA mass, but we know that on average we added 2 oxygen atoms per reaction with OH. So we can ask questions though, like, well then, is this C10O4 species the result of multi-generational chemistry, 2nd, 3rd, 4th generation chemistry, for example, adding 2 oxygens twice, or does this tend to be, from an SOA perspective, dominated by 1st generation chemistry? And we can do that by doing things like turning off 2nd generation chemistry. Right? We can make most of our grid unreactive, and we can explore these types of things. And so if we do that in this case, where what I have now, the black line here is the simulation we were looking at before, the best fit to the chamber data. And the red line here is actually if I turn off all 2nd generation and higher chemistry. And in this case, what we see is the difference is only about 20%, which actually suggests that in this case, most of this SOA mass is being formed by those species that added 3 or 4 oxygen atoms in one step. It's not being added from adding 2 twice. So it's really mostly first generation chemistry that's dominating alpha-pinene SOA formation. At least this would suggest that's the case. So we can explore these types of things and maybe gain some insights as well if we think that we have a realistic parameterization. But just to contrast that for a second, so here's a simulation or a comparison with observations for endodecane here. So this is C12 alkane. And same thing, SOA versus time. Observations are the points, and our best fit is in black. Again, we can fit the data extremely well. We can look at our distribution of oxygens. In this case, now we see we're predominantly adding 1 or 2 with some small amount of 3 and 4 being added per generation, per OH reaction, which again makes reasonable sense based on the chemistry that's going on. And so, but now again we can turn off the second generation and higher chemistry. And in this case, unlike our alpha-pinene plus OH system, in this case we see that most of our SOA formed is actually from multi-generational chemistry. It's not from these first generation products. And so whether you need to really consider the multi-generational nature of SOA formation is dependent on the system that you're looking at. At least that's what this would suggest. And so it may suggest that things like the 2-product model may prove more robust for some systems than others because it doesn't necessarily need that multi-generational chemistry that's occurring. Okay. And just to give you a sense of how well we can do using this same general model for a bunch of different systems. So here's just a variety of different conditions. We have dodecane high and low NOx. We have naphthalene, xylene, toluene, alpha-pinene under high and low. We can use this model generally at least to fit our data fairly robustly and try to learn something about all these different systems. So one of the things that we can also do that's nice is that the SOM, because it has this multi-generational aspect to it, it's really good for thinking about the time-dependent evolution of SOA. And we can do this in a somewhat chemical framework. And so we can do things like extrapolate out to longer times in a way that you can't necessarily do easily with just a 2-product model where your products are no longer reactive. And so what we're looking at here is I took my best fit to dodecane, and I just kept running it at the same OH level for longer and longer. And you notice this turnover in the concentration eventually. And that's because you're actually chewing up the gas phase. You're slowly chewing things up, turning it into CO2 eventually downstream. And that starts to lead your aerosol in an absorptive partitioning framework at least to evaporate. Right? You're getting evaporation through chemistry, which you're not going to get in a 2-product model. You're going to miss that. And so, in fact, we can basically, we could fit our observation as if it were a 2-product equivalent model, which is the same thing as saying, I'm going to turn off all later generations of chemistry. I'm only going to have first-generation chemistry. If we fit the data to a first-generation model and then extrapolate, indeed, we do see that your aerosol only goes up over time as you keep reacting more and more, and that's because your products are never getting reacted away. You're only producing more SOA. You're never chewing it up. You're basically not turning things into CO2 eventually. And so we like to think at least that we're capturing more of the actual behavior in what's going on. And I should mention Gecko as well sees things like this. You do start to see turnovers in your SOA formation. Okay. But I do want to make a point. I mentioned earlier things like the volatility basis set when they add aging, right? I said they're probably double counting to some extent. And we can basically do that here, right? So now this red line, I've done a 1-generation fit, which we can sort of think of like fitting a 2-product model or a VBS fit to the data, right? And then I can turn on aging, right? I can just turn on aging using those fit parameters. And you get something like this, okay? If you turn on aging for this system, which I'll admit is a dramatic example, there's other ones that don't do this nearly as much. You get large overestimates of the SOA. And this is sort of what the 1D BBS plus aging does. And I just offer this as a caution for people who just add aging reactions to something that has already been parameterized to fit chamber experiments, which inherently incorporates the aging reactions. You can't add them again. You're going to overestimate things. Okay. So what have I actually been doing here, though? So in my time at NCAR, I've been working with Alma and Julie and Sasha to think about how we can use the Gecko model, which is this chemically explicit model. It retains all of the possible chemistry. Granted, it has to make approximations along the way, but it's using the best chemical insights that it has, and can track the evolution of all the functional groups and other species involved. And the question is, can we use that to then guide kind of, let's say, refinement of this intermediate complexity model to say the parameterizations that I have, some of them I just kind of made up. And the question is, did I make them up well or not? I tried to, but we can start to test those types of ideas. And so we can think about questions like, I assume a fixed decrease in vapor pressure per oxygen added, and I assume it's time invariant, right? Which assumes that basically your functional group contributions are constant with time. Probably not true, but we can start to explore how important it is to consider those types of things. We can consider constancy of functional group addition, vapor pressure questions, how constant our rate coefficients are that are describing the movement through all of this space, and how well I've estimated those rate coefficients based on Gecko simulations. And so what we're going to do is we're going to take this GECKO-A output, which again has thousands or millions of species, and we're going to bin it into the same grid framework. We're just going to throw away, well, we're going to remember some of the information so we can look at it, but we're going to basically bin everything into this carbon-oxygen framework and calculate time-dependent mean properties for one from some of these simulations to compare with the mean properties, which basically the statistical oxidation model is all mean properties, so we can compare those two. And we can compare with the SOM parameters, and we can look at the time dependence then also of the Gecko output, but in the framework of the statistical oxidation model. And so this is what we're working on, and we're still trying to figure out how to compare everything. So I'll just give you one flavor of how we're looking at these things. So we've been looking quite a bit at the dodecane plus OH system under low NOx conditions. And what we're looking at here is rate coefficients. So we've taken the rate coefficients associated with each of the gecko species, weighted them by their gas phase concentration. So we're getting a weighted average rate coefficient binned into the SOM species bin, so carbon-oxygen number only. Okay, so we've binned all of those, and I'm just looking here because we're dealing with dodecanes, so I'm looking at only C12 species, just to keep this tractable. And looking at this as a function of the number of oxygen atoms that have been added to this C12 species. So I don't have C12 0. Oh, I do have C12 0 on here. So that's dodecane. So not surprisingly, it's flat as a function of time in our Gecko simulation. But then we can keep going. And when we add one oxygen, we actually see, well, it's fairly flat with time as well. If we add two, though, we see generally flat behavior here. But then it drops substantially over time. And three, well, sorry, these colors are hard to distinguish, but the basic picture is that things are changing. And the question now that I have in terms of trying to think about how well SOM works is, how much does this matter? Can I potentially parameterize something like this into it without making it too crazy? So we're working towards that. But the nice thing that Gecko does, besides allowing me to just look at this, is we can understand why. And not surprisingly, it's because the nature of the functional groups are changing for a given species. So here's just one example for C12O4, okay? And then what functional groups make up that C12O4 species. And so here we see that early on in the reaction, and I have this in log time just to accentuate the early times. We see that we have a lot of hydroxide groups, a lot of alcohols, as well as a fair amount of nitrate, even though this is a low NOx simulation. I
I'm having a little trouble visualizing one oxygen, one carbon,
one oxygen.
alcohol, but how do you get an alcohol out of those other things? How do you do that?
Well, these are 4 oxygen. This is C12O4 now. Yeah, in fact, yeah. If this is C12O, I think it's all this color. Yeah, so from Gecko. And so, but we do see in this case the ketones come in later. Also, peroxides come in, and you can really see this is the rate coefficient. Then here on the right-hand axis, you can really see that it varies as this composition changes. And all we're looking at is composition changes, right? So now we know this at least, and now what we're doing is exploring how much does this matter to how robustly how robustly we can develop the SOM. So that's what we're exploring now, is trying to basically figure out, can we use this, how can we use this to make as robust a intermediate complexity model as possible. Just to give you some perspective on this, throughout this entire space of oxygen-carbon number. So here now I have this graph, and these are colored by the rate coefficient. It's about a 1 order of magnitude range, with red being higher rate coefficients, blue being smaller. And this is the GECKO-A that you get averaged over the entire simulation. Again, we know that they're changing over time, but averaged over the entire simulation, you get something like this. This is kind of what I had come up with for my parameterization. Not horrible, but it's not perfect by any means. So working to understand this variability. And so this is the type of thing that we're trying to explore, to understand, how well does this general framework work. Okay. So I want to finish with one other thing, though. So that's our basic model formulation. That's what we're trying to do here, is to develop a hopefully robust intermediate complexity model that is hopefully usable within a regional modeling context. But I want to turn to a question of both SOM as well as 2-product models, VBS, whatever, are really only as good as the data to which we are fitting them. Okay? They're only as good as the data to which we're fitting them. Now, we could always fit them to Gecko, assuming that Gecko is perfect, which is always nice to think, but maybe that's not true. So we want to think about I want to think about how good are our measurements, and reminding ourselves that models, regional scale models, do tend to underpredict SOA formation. So what are some of the solutions that have been proposed? Well, one is to increase emissions of either stuff we know about or add new things to our model and make more mass out of new things. As I mentioned, we can add aging reactions, but I would contend that depending on how you do this, you're double counting. But I want to explore something different here. I want to explore gas phase wall loss within chamber experiments. Oh, my thing is not popping up. Forgot to make my thing go away. Anyway, gas phase wall loss, I think, is the type of thing that has been forgotten about for quite a while. It keeps coming back in vogue and then out of vogue, and people keep forgetting about it. So chamber experiments now are routinely corrected for particle wall losses. Like, if you do a chamber experiment and you don't correct for particle wall losses, then you shouldn't be a scientist. Okay? But so everybody, what I mean is everybody does this. Okay? Wall loss, gas phase wall losses, though, is something that no one corrects for. Yet, as early as the 80s, people have shown stuff goes to the walls. Gases go to the walls. It's an indisputable fact. The question is, how much do they go to the walls, and how important is that? How does that impact the SOA formation? Okay. So what we can do now that if you have a time-dependent model, because that's an important component, is you have to have a time-dependent model, because your wall losses of gas phase is going to be time-dependent. And so what I've done is I've put gas phase wall losses into the Statistical Oxidation Model framework. And I've done this using results from Paul Zeman's group, this very nice paper from Matsunaga and Zeman, kind of reminding the community that wall losses are important. And one of the key things that they found is that the gas gas phase wall losses seem to be reversible. And so the extent to which stuff goes to the walls depends on the volatility of the species involved. But the rate coefficients tend to be independent of the individual species because they're mostly determined by just molecular transport through the boundary layer near the walls and mixing within the chamber. But how much goes to the walls depends on what that species is. Okay? So it's pretty easy to, anybody can do this. You can put this into your model. And then we can start to explore how much gas phase wall losses matter. And so I'm going to do this for my favorite system here, dodecane plus OH. And we're going to just include gas phase wall losses. This is what you get. If I just turn on wall losses with, I'll say, estimated, but what I think are reasonable parameters for the wall loss rate, the amount that you lose is immense in this simulation. Okay? Now, I will say I've tried to do this for a whole bunch of different systems now, different precursors, different NOx levels, things like that. Not everyone is as dramatic as this. I like to show dramatic examples. But gas phase wall loss cannot be ignored, right? So you can do this in one of two ways. One, you can run your fit to the chamber with wall losses off, and then turn wall losses on, in which case your aerosol will go down. Or you can do your fit with wall losses on, and then turn wall losses off, and your aerosol will go up. And so this case was the first one of I fit to the chamber data with wall losses off, and then just turn it on. And so the amount of aerosol formed goes down. Does that make sense? Yeah. And it goes the other way. Yeah. But my point is simply that wall losses matter. Again, this is the dramatic example. In fact, if you do this the other way, it doesn't look quite as dramatic. It's more like a factor of 2 or 3, than this very large factor of 10. But nonetheless, it very much matters. And this is something that has basically been ignored. And so I think that this is something that's very important that we need to think about more going forward in terms of using aerosol yield data and parameterizing models and using that within like regional scale and global scale models. And this seems to me at least like probably part of the solution for why SOAs it seems to be underestimated within regional models. Not everywhere. It does. One interesting thing that you find, and this is for, just to pick a different system here, the alpha pinene plus OH system, a little complicated here, but it does change the parameters that you get out of the SOM fit as well. So this is 2 fits, both fitting to the same chamber data, one with wall losses on, one with wall losses off. And what you see is that the distribution of oxygens that you get here is a little different. I mean, it's not dramatically different by any means. But in fact, the amount of fragmentation that you need to put in to the model when you don't have wall losses is basically you have everything after your parent compound fragments. Okay, there's basically no reaction that doesn't fragment. But if you put on wall losses, then you get the more realistic solution of where fragmentation seems to increase as you add more oxygen to your species. That's because that's how I've parameterized the fragmentation. It's a function of oxygen content, but it's not 100% for everything, and it has some, maybe physically reasonable numbers, but I'd be happy to get people's opinions on whether those are reasonable or not. But yeah, you end up, in general, without wall loss, you're going to get more fragmentation. You do get a little more of these higher oxygen species. You do get a smaller contribution of second-generation products to SOA when you include your wall losses as well. So you might think that multi-generational chemistry is not as important as it might actually be. So these are just some of the implications of including wall loss in an SOA fitting exercise. And I want to finish with this point. So this is from a paper from a few years ago using the Gecko model and comparing to alpha pinene plus OH experiments from the Caltech chamber. So these are the experiments, and these are the Gecko results. And the different lines are different parameterizations for how you relate structure to vapor pressure. Okay? And it was found in general that the Gecko model was overestimating the amount of SOA. And I would say, okay, Gecko doesn't have wall losses, or didn't, I don't think, didn't include them, at least at the... Oh, you did include wall losses. Oh.
You also get a factor of 20 reduction.
Yeah. Yeah, so it's about how it depends on how you parameterize it. And so I think that this is probably just a wall loss issue. And again, Gecko's not the perfect model, but it's probably giving us an indication that there's a problem with the chamber experiments. Or maybe not a problem, just something that we haven't yet accounted for. Okay. So just to conclude, I think the statistical oxidation model that we've developed, we can use it to fit a variety of photochemical oxidation systems. I showed a bunch of examples very quickly for low and high NOx conditions, alkanes, aromatics, biogenics. So we think we can use it fairly generally. That's at least our hope as we move forward and test it further. I guess I have an extra E there, but gas phase wall losses can play a very important role. Again, I will say I showed an extreme example, but a lot of systems do show the same thing, and it really depends on how you run your chamber and the nature of the experiments that you do. But you can start to explore that if you start to include these types of things in your fitting exercise. So where are we going now? Really, right now, near term, I want to build on what we've been doing here, using Gecko to really to try to make the basic formulation of the SOM as robust as possible, so that we can hopefully believe some of these results. Say we have a realistic framework for simulating things. We are working to actually implement this into a 3D model, integrating it with SAPRAC, but separate from SAPRAC actually in the end. And so this is work in progress. Things that we haven't included here is exploring the fact that there's a variety of experiments that suggest that absorptive partitioning may not always be the best descriptor of SOA, in part most likely due to a lot of oligomerization or condensed phase reactions, but these are the types of things that we're exploring now. And also, you might have noticed we ignored aqueous chemistry, which is also a very important aspect of SOA formation in the atmosphere. And so some things that I want to pursue further is, can we parameterize solubility within the same space? And I think Gecko, actually comparisons with Gecko, provide us a good framework in which to assess that, because they can calculate things like Henry's law coefficients and everything like that. So that's kind of where we're headed. And thank you.
All right, we have about, I'd say 5 to 10 minutes for questions. I can start with the first one, if no one else does. The toluene, you showed way back several different compounds, and I noticed that toluene did a really interesting sort of like multi-bump in your fit. Was that...
That's the OH.
That's the OH?
Yeah.
Like added in at different intervals, or...
So low NOx and high NOx experiments, the more recent ones in the Caltech chamber, tend to be done in very different ways. Low NOx is done by adding hydrogen peroxide and photolyzing it. You can get a very stable source for hours at a time at like 2 × 10⁶. For high NOx, they put in methyl nitrate, I believe, or HONA. But photolyze it, and it goes down really, really fast, and depends exactly on what your lights are doing at any given time. It doesn't. It's very sensitive to any fluctuations, I think, during the warm up. And so, if you look at the VOC decay from the chamber, that's what the OH does. And so, I have made a point to just make sure my OH matches exactly what the chambers do, so that that's not a source of uncertainty.
So thanks for this talk, Chris. A lot I want to talk to you about on Wednesday when you come up. But for now, so you have 6 parameters you're fitting. How unique are these best fits considering you have 6 free parameters? And then related to that, you said you sort of need 1 fit per class. Some of these are probably in the same class for a parent molecule.
Mm-hmm.
Do you get similar fits in the space between the different parent molecules?
So that's what I'm working towards. So for the alkanes, I've done a bit of that. We have, well, I have a bunch of results for C12 compounds, branched versus cyclic versus linear. And they're similar but not the same, which is, I mean, the idea that the fits will be exactly the same is going to be an approximation always. And so what I want to do, and just trying to get the data to do it, is to do this over a range of carbon numbers as well as structures. But I think it's going to work out. And we can also do that by fitting to Gecko as well. We can actually do this with Gecko output, and that's where it's very powerful. As soon as you change NOx, the parameters that you get are totally different. And that's something that we're still trying to figure out how exactly we're going to deal with moving between high and low NOx in this space. But I can tell you that this one and this one have very similar fits. The fits for a given compound, I would say, are marginally unique. They tend to, certain parameters have more play than others. So for example, the vapor pressure decrease and the extent of fragmentation do offset each other a bit. And what I found is that some systems are more sensitive than others in terms of wanting particular answers. One of the things that we are trying to do in order to constrain this further is to use not just total mass data, but to use things like the oxygen to carbon ratio that comes out of chamber data, because we actually have oxygen and carbon, so we can include that as part of our analysis, and we generally get pretty close for many of the systems. So we're looking at that as well as looking at things like in Gecko, how well do the SOM simulated species match with the Gecko bind species. Again, that's going to be subject to whatever limitations there are there. But also there's more and more online measurements coming with like the Movi Sims instrument or Figaro Sims that give, and PTRMS measurements that give us information on how individual species are moving, and we can start to look at those. And we're doing that. It's just, yeah, data limited in part.
Question in a little different direction. It's more on the publishing. So to do these fits, you actually need the time-dependent behavior and not just yields. Mm-hmm. And to go back and look at the effect of wall losses, you need a really good description of the chamber. Mm-hmm. How much of the published chamber data is described well enough and has enough supplemental data to actually go back and do corrections or do new fits other than the ones the authors did?
Yeah. So wall losses, gas phase wall losses, I can get them close for any chamber, but how close is the question? And really it's I think I have a cartoon here at the end that I threw in. Oh yeah. So what are we dealing with? We have our chamber. We've got turbulent mixing in the chamber. That in some chambers they have fans and other things that make this really fast. Others they don't. And it's driven really by thermal gradients. Some have more stable temperatures. But you have some turbulent mixing parameter. And then you have some boundary layer at the surface that molecular diffusion is going to control. And we can estimate diffusion coefficients for these compounds. What we don't necessarily know is the mass accommodation coefficient. I wish I had my calculations on here, but you can show that at least if you separate this into 2 terms, this term is actually reasonably well known, and then you're limited more by this term, unless your mass accommodation coefficient gets too low, below about 10 to the minus 7, then it starts to deviate, and so it's a question of what is the value for a VOC uptake. But I think we can get estimates, and I think if people can characterize more chambers in this way, then maybe we'll see how robust any such estimates of historical chambers might be. But the numbers coming out, the few numbers that have come out are on the order of kind of what I've estimated for the Caltech chamber. I estimate right around, somewhere around 1 × 10⁻⁴ per second is the wall loss rate. But it's a factor of 2 on that.
Chris, if you could go back to the slide you were showing before with the yields of all the different species, just something maybe that you've tested that I was curious about. When you think of running your model beyond the point in time in which you have data, for the dodecane system you showed, your prediction of this peak and what happens after that, if you say take the metaxylene data, but only keep the first 5-6 hours of the data, fit your model to that, can you then predict what happens later on if you withheld that data from the fit?
I have not done that, at least not extensively. But that is a very good question. Yeah, I mean that would be that is an important question. How much data do you need to get a robust fit? And that I'm not sure of. I would say that's something I'll do. And the other thing though is that hopefully the parameters that we have, while not perfect, have some physical basis. And so by looking at those as well and thinking about the chemical mechanisms involved, we can at least say, is that close to reasonable? And then maybe we'll trust the fit. But that's a very good idea. Thank you.
All right. Do you see the question?
Hi, this 2D comparison plot that you showed between the SOM model and Gecko, where you showed reactivity, and that was for what species? Dodecane, okay.
Dodecane.
So what do these plots look like in terms of volatility? How do they compare? You showed reactivity here, but
I don't have that. They actually compare pretty well in general. I think we were looking at that the other day, Sasha and I. And I mean, they certainly have the same general features. As you increase carbon number and increase oxygen, volatility goes down. So here's your low volatility species. Here's your high volatility species. And they get that, right? But they get pretty reasonable.
I think it's a later question. When I look at the bar diagram of the number, if I look at your bar diagram with a number of functional groups or oxygens on every particle molecules, I guess.
Like this?
No.
Oh.
There's a bar. Yeah, that one. Okay. This is for alpha pinene. Can you have the one for dodecane? Okay. I was very surprised in that plot, low NOx, that the one oxygen species with 12 carbons on it would be the most abundant. Is this in the gas phase or in the particle phase?
That is not most abundant. That is most likely to form. So at early times, if I had a distribution, I could put curves on here for every species. So at early times, yes, C12O1 is most abundant.
I guess C12O1,
at later times, it's not.
I don't see how you can make it from low NOx, from C12 alkane. There's some very indirect ways of doing it at low NOx with
we see it. I mean, we have it in
peroxide
Gecko.
photolysing to the alkoxy or but I don't know, 2 out of 2 reactions. That's little stuff.
So I mean, I don't have the graphs here, but we've looked at basically
so you
this.
compare with Gecko.
Yeah, we've looked at that, and it's not. There's actually for the C12, 03, 04, and 05 actually show pretty good agreement in general between Gecko and SOM, but that C1 species is off in terms of timing, but the amounts that are formed that you get kind of surviving are on the same order of magnitude in Gecko and SOM. They're not perfect and the timing's not perfect. But comparing each of those individual species is something we've been working on. It's just, there's lots of species and it's tried to fit to all of them simultaneously, and I can tell you that it's not, SOM is not a robust enough framework to allow me to fit every single one of those species compared to Gecko. I can't, do a multivariate fit of everything. It doesn't work. Yeah, I mean, so back to the question earlier about how unique the fits are. There is a little bit of slop between adjacent bins, but in general, it's a fairly robust at least fit. And so again, it's a question of how well do we actually capture the chemistry that's going on. Yeah. I'll answer quick.
When you're talking about the wall losses, you specifically mentioned gas-based wall losses.
Mm-hmm.
Two-part question. One is, have you taken into account the volatility of the species that goes to the wall in terms of how much that species the wall losses? The second part of the question, you specifically mentioned gas-based wall losses, but what about electrostatic losses of particles?
Sure. So second part first, particle wall losses. The people who provide me the data correct for wall losses based on measured deposition rates, size-dependent deposition rates. So they correct all the data based on the observed loss rates of the particles to say, okay, this much was lost to the walls over time. But part one, yes, we account for the volatility. Because the amount of stuff that's on the wall, the equilibrium wall concentration that you get, depends on the vapor pressure of the compound that you have, adjusted for some activity coefficient for basically dissolution in Teflon. And so you can think of it this way, where the rate coefficient for transfer on is somewhat species independent. It just depends on, it's going to depend on how much do the diffusivities between the individual species differ to get them to the wall. But the rate coefficient for evaporation is going to be species dependent and proportional to the vapor pressure.
I think we're out of time. I don't know if it's working anymore. Sorry, I'm going to get to talk to him when you're. I think it's a question. What did you provide for these models?
It depends on scale, right? So Alma has a very nice approach, which is, I complained about the VBS adding aging, right? Because I do think that's a problem. But there's no reason that you can't include some aging terms as part of your VBS fit and just inherently have that. And that's what Alma's working on, fitting the Gecko data. There's no reason that can't happen, and maybe that ends up being robust enough. The question is, does it capture enough of the chemistry to be robust? That's the thing. We think that the way that we frame this, maybe this has more potential for being a robust solution, but we'll see. But I think things like that are going to be, the stuff that she's working on is going to be powerful, certainly in the near term, for making a better simulation. But also, I think potentially a revision of yields based on wall loss and just increasing yields of certain species. But it's not going to be factors of 2 or 3 or 4 for everything. And my calculations so far suggest anywhere between 10% and factors of 4. So but I think some revisions that way will be necessary soon, hopefully, and maybe make things better. Maybe not.